Hello all, and welcome to the next video in our Introduction to X-ray Diffraction series. This is Chapter 2, Part 2, and it covers symmetry. So we're going to start with the basics, and that is translation. One type of repetition, lattice translation, underlies the periodicity of 1, 2, and 3-dimensional nets. The surroundings of each lattice point are identical, not only in kind, but also in orientation. So what does that mean in reality? So in one dimension, let's pretend that we have these two dots. We will pretend that they are atoms. And they're separated by some distance a. Now if we take these two atoms and then shift them by that a distance over and over again, we start to make this 1D array of atoms through translation. If we look at 2 dimensions and we start translating in both dimensions, we get this new array of atoms. And then finally, if we look in 3 dimensions, we can really start to see how translation can begin building 3-dimensional volumes. So that's all translation is. Very simple, straightforward. Now let's look at our macroscopic symmetry elements, where symmetry is the second type of repetition required to define the periodicity of 2- and 3-dimensional assemblies of atoms, ions, or molecules comprising crystals. So here we have reflection, we have rotation, inversion, and roto-inversion. So let's look at each one of these in more depth. If a body is symmetrical with respect to a plane passing through it, then reflection of either half of the body across the mirror plane will produce a body coinciding with the other half. Now, that's a lot of fancy words to explain a very simple and straightforward concept. So here we have just a cube, and here we have an atom at a corner. Here in blue, we have the mirror plane. So if we want a reflection symmetry with this atom, we will move it in a perpendicular direction towards the mirror plane. And we'll say that we're moving at some distance a over 2. We then take that and continue moving it along that line another a over 2 distance until we get to our new position. And sure enough, that's what we have for a simple cubic structure. Everything on the left-hand side of the plane is mirrored by the right-hand side. So pretty straightforward so far. Let's look now at rotation axes. And a body has n-fold rotational symmetry about an axis if a rotation of 360 degrees divided by n brings it into self-coincidence. So what's that mean? Basically, if we spin about an axis some amount of angles, then the atoms will basically form the same arrangement as they originally did. So here we have another cube. I've just kind of included the top atoms here. At each corner. Here we have the rotation axis going straight through the top and bottom to the centers of the top and bottom faces. Now sometimes the symbol is represented as a parallelepiped, sometimes it's a square, but this indicates a 4-fold axis. So because it's a 4-fold axis, n equals 4, so then 360 divided by 4 means that we need a 90-degree rotation to bring everything back into coincidence. Now you're going to see these videos I'm about to show you over the next, this slide and then 2 more. The sample I'm using is not a cube. I do ask that you please pretend that it is a cube. For some of these, that's technically the only way that this is going to work well. But let's go ahead and watch the video. So we see for the 4-fold axis, the axis goes through 2 opposite faces. So I'm going to put my finger in the center of that face, and then in the center of the bottom face. And that is going to be my axis of rotation. So if we hold it like this, and we said that this is our A1 corner, if I rotate it 90 degrees, it's going to become this corner. So you're going to watch that. There we go. So that is the 4-fold axis. Essentially what we saw was that this atom, when we rotated it, became this atom. And then by symmetry, this atom here would become this atom. This would become this would become this, and we would see the same arrangement of atoms in 3-dimensional space as before we did the 4-fold axis rotation. So that's what it means when it says that it brings itself into self-coincidence. Even though we rotated 90 degrees, we still have an atom at each of these positions. Let's look now at a threefold axis that's indicated by a triangle. 360 degrees divided by 3 is a 120 degree rotation. So let's go ahead and watch the video. Now for the threefold axis, we go through the body diagonal. The rotation axis goes through the body diagonal. So I'll put my finger here on that corner, and then away on the other side on that corner. So now it's going through the body diagonal. Now what you should see is that if I rotate it, this corner should go and become this corner. So if I take that, rotate it 120 degrees, that's what I wind up having. The last one we're going to look at in three-dimensional space is the twofold axis. This means that we need a 180 degree rotation, so let's just watch the video. Now finally, for the two axis, it goes through the edge, the middle of one of the edges, through the sample to the middle of the other edge. So it starts out there, and then it should end up there, which it does, with a 180 degree rotation. So that is the twofold axis. Moving on, let's look at inversion centers. A body has an inversion center if corresponding points of the body are located at equal distances from the center on a line drawn through the center. So what's all that mean? Essentially, if we have an atom, we'll just pick this one here, the A1, and we draw a line from it directly to the center of our cube. And we'll say that this is length 1. If we extend that line an equal length, length 1, then we have to hit another atom, which we do in the case of this base-centered cubic example. If we chose this atom here, the base-centered one, we would see that it has a length 2, we extend it by another length 2, and we get that another atom is present. And really that's the case for all of the different atoms in this unit cell, which means that it does have an inversion center. Now let's end it with a roto-inversion center. So a body may have a rotation inversion axis, either 1, 2, 3, 4, or 6-fold. If it has an n-fold rotation inversion axis, it can be brought into coincidence with itself by a rotation of 360 degrees divided by n about the axis, followed by an inversion in a center lying on the axis. So here we have a fourfold axis. So this A1 point, if we rotate it, becomes A2, and then we need to have an inversion point sitting on the rotation axis, which for the cube, it's the center of the cube, which actually does sit on that rotation axis line. So then if we apply A2 to the inversion center, we get A3. So this, a simple cube does have a roto-inversion center. Let's end this by looking at some symmetry operators for crystallography. This is not all of them, just some of them, and we are looking now in 2 dimensions. So we have one-fold rotation axis, which means that we just rotate the sample by 360 degrees to bring it into self-coincidence. So here we have a lightning bolt. It's very asymmetrical. So if we started rotating it, the only way it comes into self-coincidence is with a 360 degree rotation. We could even have a weird arrangement of these lightning bolts. If we rotated it, we would see that only a 360 degree rotation brings it into self-coincidence. So really, a one-fold symmetry or a one-fold axis is nothing special. Pretty much everything has it. For a two-fold axis, as a reminder, that shape is an oval. And then we see that if we rotate by 180 degrees, it comes into self-coincidence. For a threefold axis, represented by a triangle, we only have to rotate it 120 degrees for self-coincidence. Fourfold, indicated by a square, if we rotate it 90 degrees, it's self-coincident. And finally, for a 6-fold axis, if we rotate it 60 degrees, we get self-coincidence. Now next up we have a mirror. There's our mirror plane, so that we move it an equal distance from the mirror plane. But because this is a mirror, it must also be reversed. Next up we have a mirror plus a 2-fold rotational symmetry. So let's go grab that 2-fold from here, put it down here, and then we'll apply a mirror axis. Well, for that to work, we have to get these two elements, and then we see that if we follow the 2-fold rotational symmetry of 180 degrees, we get self-coincidence. One thing I will point out is that you can wind up with more symmetry elements than you think. Yes, this has a mirror plus a 2-fold, but not only is the mirror that way, it's also this way. So that's just something to keep in mind. Combining symmetry operators can produce others. So now let's look at the mirror plus 4-fold. We'll just bring that down from here. And if we now apply a mirror axis here, well, that doesn't really work. This and this are not mirror images. You know, the part of this lightning bolt on the left side is not a mirror image to the right side. So this doesn't work as is. What we can do though is take all the lightning bolts and translate them in a counterclockwise fashion, like so. We then apply the mirror to each of the lightning bolts that we have in our sample. We then see that if we perform the 4-fold rotational symmetry, which is 90 degrees, the lightning bolts all come into self-coincidence. And just like with a 2-fold, we do have this mirror plane shown here, this one shown here, but we also have this mirror plane and this mirror plane, which makes it a 4-mirror plane system. And that's pretty much it. As always, Gus and I thank you for watching, and we hope you have a great day.